So here's L'Hopital's rule. Version 1. It's not going to be quite the same as what we just did. It's going to be much, much better and more useful, all right? And what it's going to take care of is this problem that the denominator is not 0, all right? So now here's what we're going to do. We're going to say that it turns out that the limit as x goes to a of f of x divided by g of x is equal to the limit as x goes to a of f prime of x divided by g prime of x. Now that looks practically the same as what we said before, and I have to make sure that that you understand when it works. So it works provided this is one of these undefined expressions. In other words, f of a is equal to g of a is equal to 0. So we have a 0 over 0 expression, indeterminate. And also we need one more assumption, and the right-hand side, the right-hand limit. Limit exists. All right? Now, this is practically the same thing as what I said over here. Namely, I took the ratio of these functions, x to the 10th minus 1 and x squared minus 1. I took their derivatives, which is what I did right here, right? I just differentiated them and I took the ratio. This is way easier than the quotient rule and is nothing like the quotient rule, all right? Don't think quotient rule. Don't think quotient rule. All right, so we differentiate the numerator and denominator separately. And then I take the limit as x goes to 1 and I get 5. All right, so that's what I'm claiming over here. I take these functions, I replace them with this ratio of derivatives, and then I take the limit instead over here. And it turned out that the functions got much simpler when I differentiated them. I started with this messy object, and I got this much easier object that I could easily evaluate. All right, so that's the big game that's happening here. It works if this limit makes sense and this limit exists. Now notice I didn't claim that that the denominator had to be non-zero. So that's what's going to help us a little bit in a few examples. Well, so let me give you a couple examples, and then we'll go further. Now, this is only version 1, but first we have to understand how this one works. So here's another example. Take the limit as x goes to 0 of sine 5x divided by sine 2x. This is another kind of example of a limit that we discussed in the first part of the course. Unfortunately, now we're reviewing stuff, so this should reinforce what you did there. This will be an easier way of thinking about it. So by L'Hopital's rule, so here's the step. We're going to take one of these steps. This is the limit as x goes to 1 of the derivatives here. So that's 5 cosine 5x divided by 2 cosine 2x. Oh, whoops. Thank you. The limit was 1 over there, but now it's 0. A is 0 in this case, right? This is the number A. Thank you. All right, so the limit as x goes to 0 is the same as the limit of the derivatives. And that's easy to evaluate. Cosine of 0 is 1, right? This is equal to 5 times the cosine of 5 times 0. And that's a multiplication sign there. Maybe I should just write this as 0, divided by twice the cosine of 0. But you know that that's 5/2. All right, so this is how L'Hopital's method works. It's pretty painless.